So we'll be beginning with our revision of the concepts of mechanics, and I hope you'll be able to follow the way I'm doing it. So let's move this somewhere. Okay, I think this is best we can do. Okay, so you are already aware of the textbook which we are using. We'll be following up with an introduction to mechanics of solids in SI unit, 3rd edition by Crandall, Dahl, Lardner and Sivkumar. This is through the McGraw-Hill. So if you want to solve any problem in mechanics, what are the steps which you take? The most common method, and you are already aware of it, is to select a system. So you have a system which you have selected. Then you want to simplify the system. What this means is that you may have a very complicated real life problem, but then you idealize some of those things and simplify the real life situation so that you can be in a situation to actually solve it. Okay. Then the third step is that you apply the concepts of mechanics and then you deduce the consequences of it. So this is where you apply your knowledge of mechanics and then you come out to your final outcome, and we'll see all these things in more detail as we solve the problems. The fourth part is the comparison. This means that whatever you have predicted as a solution to your problem, does it actually match, or is it of a similar nature that is seen in a real life? And if it is if all those four things are done, and you need a fifth step only when you cannot achieve a comparison. So in this case, you must reconsider the steps which are above. This step is only done when your comparison is not favorable. Okay, so we'll see how that happens in a real problem as we go along in this. Okay, so let's see how you would want to move ahead, and so I'll just delete this part. Okay. So there are a few terms which I'll be writing which you should already be aware of. For example, what is force? Okay. What is motion? Okay. Then through this you have many different words which come out of it. For example, deformation. Okay. Then there are other categories through which this motion can be listed as, like dynamics, like kinetics, like kinematics. Okay, and we'll see how what all these things mean, but you, from your earlier knowledge, perhaps you are already aware of what a force is, what a motion of is, and we are referring to motion of a point particle, the particle physics which you may have learned in your earlier years, and how those ideas conform to a situation where you have dynamics, kinetics, kinematics, and so on. This course essentially will be about this. Okay, so what does the word deformation mean? How do you quantify deformation and things like that? Okay, so the important part is that there is always a connection between deformation and force, and that is the crux of this particular course. Okay, how do the forces and deformation at a point relate to each other? Okay, so this is the first course which everyone learns in solid mechanics, but this is where we start. Okay, the connection between force and deformation. So let's see how that will be played out in this one. Okay, so the steps which I had told you beforehand, the 5 steps, remember, they are simplified for the sake of our learning in the language which we'll be using in this course. So for that, you have the first step as the study of forces. Then you have the study of deformations. And then, as I've said, because there exists a connection between force and deformations, we'll use the application of laws between force and deformation. Okay, so these are the 3 simple steps, and I would strongly recommend you that you follow the methods which we are using over here, and then you can be creative and imaginative about as the course progresses. Okay, so we'll always start with the study of forces first, study of deformations later, and then we'll relate them by a specific law which will tell the connection between the force and the deformation. Okay, so let's okay. Okay, so you are already aware of the concept of force, okay, and that's why we are not discussing it in any detail as such. The only sort of type of forces which we are using in this will be of either say a gravitational force or a force at a point through mechanical effects, but you must also be aware that there are electrical forces, magnetic forces, and so on. Okay, so though in this course we limit to only a certain kind of force, but force can have many different origins. However, the units and their treatment will always remain the same, meaning you have the units of say newtons in the SI system, and then there are pound force and so on in other systems. And so we'll be using the SI system in this course because we use that in our country. So if you were in America, perhaps you would be using some other system, but this is what we'll be using as a force. So for a force, I mean, you are already aware force is a vector, and hence it has its magnitude, it has its directions, and another most important part is that it must, as a vector, also follow this law of vector addition. Okay, it is the same law because of which a quantity like the angular displacement, despite having a magnitude and a direction, is not actually considered a vector because it is not able to satisfy this additive property of vectors. So that is one thing which you should really keep in mind, that a vector, other than having a magnitude and a direction, must also follow the transformation laws uh, which you are already aware of. Okay, so you are also aware of what an internal force and an external force in a system is. So, I mean, if there are two particles in a system, the forces which they exert on each other will be seen as an internal force, and their combined weight can be seen as an external force of the system. Okay, so there are things which you already know. So let's start with something which is not as common as the things which we have just discussed. So this concept is called the moment of a force, and you have a figure which you can see on the screen right now. So let's see let me just see if I can zoom this. Yes, I can. Okay. Okay. So in this figure, let F. So one of the things which you should see in this course and this book is that when I write a vector using my pen, I'll always be showing a overhead bar. Okay. But the same vector, when it appears in your textbook or the diagrams on your screen, they will be through a bold symbol. Okay, so in this figure, if you see, you have F, capital F, be a force vector applied at a point P. So look at point P over here. See, let me choose another color for now. Okay, let's go with green. So there's a point P on which you have a force F acting, and there is also a point O which is fixed. So this is the point O which is fixed in space, and there's also uh, okay. So you say the moment of a force, okay, or just go back to so you say the moment of a force, or the torque as it's called, of F about the point O. This is entirely what you would need to write. Okay, this is equal to R cross F, where the cross sign shows it's a cross product between two vectors. Here is one other side note which I would want to give. In this course, and perhaps all the courses of engineering which you study, if you ever want to multiply two things, let's refrain from using the cross sign. For example, if you want to just multiply 2 and 3, just write it as 6 without writing it like this. Okay, so that we are clear, the cross sign always means a cross product, just for that's sake. And if there are obviously symbols which you have to use, like AB is just the product between these two numbers AB, and A dot B will be the dot product between the two vectors, and A cross B will be the cross product between these two vectors. So let's use this practice so that there is no confusion in the way we write things. Okay, and this is how you define the moment of a force about a certain point. It's always about a certain point, and that point here is O. That is this vector R and cross this vector F. So you know from your knowledge that the direction of this vector R cross F will be in a plane which is perpendicular to it. So this r cross f, you can see it over here. Okay, and that's how this moment of a force is defined. Okay, so as you already know, the moment is a vector quantity, right? A product, a cross product of two vectors is a vector, and that's why the moment of a force is a vector quantity. Its direction is perpendicular to the plane determined by OP and F. The sense is you can find out using the right hand rule. I mean, you're already aware very well of how to use that rule to find the direction, and it works all the time. Okay, so now you want to find the if you want to find the magnitude of this moment of a force, what would that be? The magnitude of this would be, obviously written it in this form, and from your knowledge you already know that it can be written as Fr sine phi. Okay, where phi is the angle between R and F. Okay, so phi is the angle between R and F. Also, I mean, let me switch to blue. I think that will work everywhere. So phi is this angle over here, and you can find out the magnitude of the vector in this particular form. Okay, note that the magnitude of the moment is therefore the area of the parallelogram having R and F as its sides. So if you have a parallelogram from O, okay, we are referring to this particular, so then you have R, you have F, and then to draw this as a parallelogram, so the magnitude actually shows this particular area, the shaded area. Okay, and that's how you can geometrically understand what this is. Now let me just come back to this. Okay, so this is P, this is R, okay, F. Let's call this distance as H. Okay, from O to this line. So that is already shown in your figure. I have just shown it in a slightly more exaggerated form in this diagram which I have drawn. So H is the length of the perpendicular which you have dropped from O, and if you really want to find the magnitude of the moment, then you can also write it as H into F. Okay, so this would just give you, I mean, and you already know how this can be done. I mean, half into base into height would be giving you the half of the parallelogram, and you multiply by 2, that gives you the area of the parallelogram. So this is how you would define the moment of a force, and let's just sort of recap all that into something which is similar. Let's see. Okay, yeah. So I would have thought it would have taken me shorter to rub the screen in a digital format, but it turns out it takes the same amount of time. Okay, let's see. Okay, So the moment of a force is R cross F, and you can always I mean the scalar part of it we can write as RF sine theta. Now consider a two-dimensional structure, okay, something like this. So this two-dimensional structure which you have over here, uh, the moment of the force about the point O in this case, okay, so the moment of the force, so we should be looking at figure 1.7, this one, okay. For this case, obviously we'll be writing at M is equal to R cross F, okay, and this particular can be written also as K into H into F. So K here is a unit vector in the Z direction. So you know what the Z direction is in this case. The Z direction is coming out of the plane. Okay. So somewhere over here, and K is a unit vector along that direction. Okay, so H into F is what you have, and this is just meant to sort of give this a direction because these two quantities are a scalar. Okay, now you can also write this, and you have done this in mechanics I think several times, as if you break down this vector into its components, so xi plus yj. How do I know this? From here, okay, cross fx I cap plus fy j cap. So that's how I am able to write this, and if you carry out this cross product, you will be getting k into x fy minus y fx, okay. So you must already be aware of how the ijk's are taken in a cross product. Okay, so that gives you this magnitude, the moment of a vector f about a point O. Okay, which is acting, the force is acting clearly on this particular point. Okay, so let's see an example now. Okay, this is the example which we are considering. So you have to, in this example, example 1.1, as it's given in your book and the diagram which you have in front of you, is the determination of the moment about a line. This is sort of a slightly newer concept, and let's consider this and see how it works. So this is a crank handle which you have. Now this sort of assembly you may have seen in those juice stalls, which are, perhaps when you go to a market you see those juice stalls. They put in various kinds of fruits and then they rotate it using this handle which is coming out over here. Okay, so this is a similar sort of a mechanism, and it's called a crank mechanism because you convert this rotational motion into a translation motion elsewhere. So that mechanism is also used in automobiles, where a rotational motion eventually gets converted to a translational motion and the other way around. So you'll see this in many mechanisms as you proceed in your course, and perhaps around you, if we keep our eyes open and see how those mechanisms work, you'll see this in a lot of places. Anyways, coming back to this particular issue, the objective is to find m, the moment of a force, about the axis OO dash. So right now we are sort of progressed from finding the moment about a point to finding a moment about an axis. So the axis OO dash should be visible to you in the screen. Okay, and you have to find the moment of the force about this one. So let's first start about defining the moment about a particular point, and then we'll translate it back to the axis. So let's choose the point A. Okay, find the moment of P about A using, so this would give you RAB, the position vector going from A to B. Okay, and P is this point. Sorry. Okay, this is the point at which the force P is acting. So this is given by this, the moment of force P about point A is given by this value, and then in order to get the moment about an axis, all you have to do is find the component of the moment vector parallel to the axis. Okay, so how would you do that? You will take RAB cross P dot I. Okay, so this is a vector, and by taking a dot product with I is basically the direction OO dash. Okay, by taking a dot product of this vector with this, you are seeing the projection of this vector on this axis. So that would give you the moment about the axis OO dash. Okay, so this is how you would proceed in this particular situation, and so the rest of the part is actually quite easier, and you have already done it in your earlier course in mechanics. So I'll just briefly tell you without writing the equations. This is a solved example from your textbook, so you can easily see. Okay, so you want to take the vector, this force P, and then project it on this axis. Then you can take that either on this axis and on this axis, depending on what your situation is. Okay, so you have, I think, already done this in your first year in mechanics, so I'm not going through this part again. Okay, let's see this example, this diagram over here, and okay, so there are sort of these two uh, let's have a situation in which you have more than one force. Okay, so in earlier whatever our discussions have been, there have been only one force, no matter how complicated the geometry was. But we are now considering the cases where there are more than one forces. So when there are several forces acting, their total moment or torque about a fixed point O is just R I cross F I. Sorry, F I. And summed over. So in short, you can write the moment of all the forces about the same fixed point O as R1 cross F1 plus R2 cross F2 and so on, where R1 is the position vector of the point where the force F1 is acting with respect to O. R2 is the position vector of the point at which the force F2 is acting with respect to O, and so on. Okay, so you can do it for as many forces as you could want, or they are available. There is an interesting case in which there are two equal and parallel forces F1 and F2 which have opposite sense. So look at the figure on your left, which is figure 1.9. Here it shows a situation that there are parallel forces F1 and F2, and they are acting in the opposite directions. So first of all, this configuration is called a couple. Again, you must be aware of this from your earlier knowledge. And you want to find the sum of the moments of F1 and F2 about O. So look at this point O hanging up above like here, and you will see why we are taking this point O in this way. Okay, why are we not taking of some nice point like say in the middle, the midpoint between these two forces, lines of forces and so on. So it's hanging somewhere above like that, and as you are already aware that the moment of these two forces about O will be equal to R1 cross F1 plus R2 cross F2. R1 and R2 you can already see in the diagram which you have. Now you are already aware of the triangle rule of vectors, so you should be able to write that R. So if you look at this triangle O, this triangle, okay, you can write R2 plus A is equal to R1. Okay, so you want to now substitute this over here, and then you can write it as R2 plus A into F1 plus R2 into F2. Okay, that would give you R2 into F1 plus F2 plus A into F1. Now, since F1 is of the same magnitude as F2 but acting in the opposite direction, you will get this value as equal to 0. So the moment of these two equal and opposite forces is actually equal to A into F1. And what is A again? You can clearly see A is the displacement, the position vector going from an arbitrary point on F2 to an arbitrary point on F1. Okay, so it's going from this point to this point. this is important. Why is this important? Because it is independent of O. Okay, so wherever your O is, it does not matter. The moment of this system, where you have forces which are equal but acting in opposite senses, is independent of the position about which you are trying to find. And there are widespread sort of applications of this particular situation. Uh, so let's look at this in a slightly more detail. Look at figure 1.10. Okay, and then you have it. So there are two forces acting in this form, a couple as we have defined, and then this can be replaced by a moment vector. You have again already done this in your first year mechanics course, and hence I am writing it in this form. Okay. Okay. So we will use these concepts quite often when we have to solve some complicated problems and we want to replace a couple system by just one point. And what we do is we replace those two equal and opposite forces acting at a distance by a small moment acting at a point, which is A cross F. Okay, so that's where we sort of write the couple as a moment vector. There is another way to define the moments whose axis is perpendicular to the plane. So let's see this figure, figure 1.11. Okay. So in this particular figure, you sketch the plane figure acting on by a couple whose axis is perpendicular to the plane. So you have the x, y and z axis, and then there is a couple which is acting in this form, and then this can be represented in this particular way. Okay, so this is just like a two-dimensional representation of this problem, and this will be very rigorously used in bending analysis, which we'll be see bending of beams and things like that. So we'll see how a couple like this is used. And you must remember, if you are able to write a couple as a moment, okay, and you can always take it back to the forces as well. So a moment can be written as a couple as well. For example, in this case, you see a moment over here, you can replace it by a couple, in which you will have two forces acting at a certain distance from each other. Okay, and but the magnitude is the same. So you should think about now, this is where the question for you is, where are those two F1 and F2 acting in this case, in this diagram? Okay, so this may take some thinking, but this is the only way to ensure that you understand. So if you want to sort of replace now the moment with the couple, how would you draw this diagram? So you can get to that and see how it works for you. Okay. So there are some other uh, concepts which we'll be just going through quickly because you have gone through them in details in your earlier course in mechanics. So let's start with something called the equilibrium. Okay, so you are aware of the Newton's law of motion, and it says that a particle has no acceleration if the resultant force acting on it is zero. You say that if this is a situation, it's called an equilibrium, and the study of forces is in this case called statics. If you don't have that, then you call it as dynamics. I mean, if there are accelerations happening, then you call it as dynamics. Okay, so the sum of all the forces would be zero. Okay, so there is also this difference of internal and external forces. So if you have these, say, a system like this, and then you have particles of this nature, and each one of them, as you are aware, will be exerting a force on the other, and so on. Okay, now these are all internal forces. The arrows which I show within the circle are all internal forces, but any force which I take it out is an external force. Okay, and so on. So you say that if a set of particles is in equilibrium, the sum of the external forces must be zero. Okay, so F2, the internal forces don't matter over here. Okay, so it's in equilibrium. If your system consisting of particles is in equilibrium, meaning the sum of the external forces must be zero. Now you also, so this was about the translational part, and then there is a rotational part in which you say that there is no angular acceleration, and that happens if a set of particles is in equilibrium. The total moment of all external forces about an arbitrary point O must be zero. So R1 cross F1 plus R2 cross F2 Rn cross Fn must be zero. Okay, so both of these conditions have to be met if you want to call your system to be in equilibrium. Okay, so the internal forces will cancel out themselves, internal moments will cancel out themselves. So you, as a engineer trying to solve a problem, you only have to consider the external forces and the moments due to those forces. So this is referred to as 1.5 in your textbook. This is referred to 1.6 in your textbook. Why am I giving you these numbers? Is because for the most of your book, the text reads, which you must read your textbook. Don't like shy away from reading the textbook, and you should have a lot of patience reading textbooks. I mean, it is an habit which all of us must get into. So 1.5 and 1.6 equations will be referred time and again. So you must by heart this right away. What is equation or the condition 1.5 and what is condition 1.6? Okay, they are called necessary conditions for equilibrium. Okay, if your system is in equilibrium, 1.5 and 1.6 must be satisfied. Okay, there is no other way to put it. Okay, now this is easy when you have the particles which you have seen before. Okay, something like this. What about solids which can deformed? and we are studying that because that is what we require in our course. So let me show how these equilibrium conditions are utilized when a solid can be deformed. So if you have a solid, okay, this is say a three-dimensional solid which is deformable, meaning it is not rigid. What does a deformable mean? When you apply forces on it, it will show deformation. A rigid body will not deform. Okay. So if this is a deformable system, in this case, the equilibrium is said to exist when other than for a rigid case. What was the rigid case? That the external forces and the external moments are all adding up to zero. For a deformable body, that has to happen, plus there is an additional condition for it to be called an equilibrium, that on every possible subsystem isolated out of the original system should all be sets of forces which satisfy 1.5 and 1.6. Meaning, if you take a subset like this, okay, this will also satisfy 1.5 and 1.6. If you take any other interval, this will also satisfy 1.5 and 1.6. This condition, this additional condition is not required in a rigid body, okay, for equilibrium, but for a deformable this is required. Okay, so this is the additional condition, that you will have every possible subsystem which is isolated out of the original system should satisfy these 1.5 and 1.6. Okay, and this is where we sort of understand what deformable bodies are and become comfortable with this idea, because this will stay with us for a long time. Okay, so one of the other sort of closing remarks before we sort of stop this lecture right now is that we want to learn and apply these equations 1.5 and 1.6 for the problems which we have for deformable systems, as you will see, but this is all at something called a continuum scale. What does this scale mean? That you cannot actually say that this particle is different from that particle and that particle is different from this particle. You know that, but you don't distinguish them when you apply this. For example, you look at anything around you, a desk, a pen, a pencil, a wall, and so on. You see them as a continuous solid, despite knowing the wall around you is actually made up of very small granules. You will still see it as a continuum system, as a continuous system, and hence you are able to apply these concepts what we learn in this theory over there. Okay, if you go to a smaller scale, meaning if you go to a scale where you can start seeing those small particles, and then you want to sort of apply what we are doing it, then you cannot say that those systems are in equilibrium. And for non-equilibrium systems you have something called statistical mechanics. Okay, so when you learn say a course in your material science, you will see that how a piece of iron or a metal which looks continuous is actually made up of very small grains, or depending on which level you want to see it, then there are grain boundaries and so on, and this whole concept of equilibrium may not apply then. So it seems it's a good place to stop since the battery is also about to go and we have already done our 50 minutes. I'll see you in the next lecture and continue from where we have left now. Okay, so thank you.